Right, the topic of this lecture is arrays. These are C data containers that we're going to use quite a bit this semester. Well, first, in this first part of the lecture, we'll talk about one-dimensional arrays. After we learn to work with them, then the next lecture will go on to cover multi-dimensional arrays. Lecture after that, we'll talk about variable length arrays, and then we'll talk about how to generate random numbers, because we'll use random numbers quite a bit to actually store data in arrays and be able to test it. One-dimensional arrays. An array is just a data structure that contains a collection of similar data values. All the data values in the array are going to have the same type. We'll refer to those data values as array elements, and then we'll access their position. We'll read and write to them using their index position within the array. Right, so it'll be a relative position to the start of the array. All of the array elements will be stored consecutively in memory. So if we create an array of 7 elements, the first element will be stored in array at index 0. So we always start counting in programming in C with 0. Right? So the first element, index 0. The last element, so there's 7 elements. We have 1, 2, 3, 4, 5, 6, 7. The last element will be array at index 6. So the final index is always 1 less than the number of total elements in the array. In order to declare array, it's very similar to declaring a variable. Right? We have to have a data type. We have to give it a name, so we follow the C identifier naming rules. And now we also have to give it a size. We have to say how many do we want in the container. So a general form of the syntax here would be data type, name, and then the size goes inside these square brackets when we declare it. Here are some examples. If we want to declare an array that has 5 integer elements, well, the data type here is integer. So here's our type, int. Right? We can give it any name, so I called it any name here. And then the 5 in brackets means I have 5 elements in my array, and I've allocated memory for that many. We can do this with any data type. In this case, we use float. So declare an array of 3 float elements, data type float, just happen to name it F array, and the size here is 3. Finally, here's an example with char. The name of the array is called name, and it has 27 elements in it. So once again, when you declare an array, we now have 3 pieces of information: the data type, the name, and then the size. Right. The array size is constant. Once we declare it, we cannot change it. So right here, we've declared an array of type int. Right. The array name is scores, and there's 10 elements in it. We cannot change it later. We also can't declare it like this. We can't leave these brackets empty and give it no size. So that's illegal. Right. This is legal syntax in terms of I can declare an integer variable named n. In the same line, right, followed by a comma, I could say array of size n, but I don't want to do that because n at this point has a garbage value in it, and the size of my array would be unknown. The compiler likely won't flag an error for that, probably a warning, right, depending on the warnings you have set. So you want to avoid this. While some syntax is legal, it leads to unpredictable results. Remember, whenever you declare an array, if you're using a variable such as n for the size, make sure that n has a valid value. In this case, once again, here's a similar syntax, but we now have predictable results. We declare n, we assign 10 to it, so now when you declare this array, you know that there are 10 elements in it. And so always make sure if you're using variables that they've been initialized to some value before you declare the array. All right. A lot of times we'll use pound defines, or we'll use constants then to declare the array size. So pound define array size is the name of the macro here, is 100. So anywhere I use array size in the code, it substitutes in the value of 100. All right, we'll see as we work with arrays, we're going to have to know their length and their size quite often. So using a mnemonic, a variable, allows us to use that same mnemonic throughout our program. If we ever need to make changes to it, we make changes in one place instead of several places. You can also declare arrays with a constant identifier. So back here, this is a preprocessor directive. Pound define, we refer to this as a macro. A constant identifier, right? We use the keyword const in front of it. That makes this variable a size read only. We can't write over it later. And we can use that as well to now declare size. We've stored 5 in a size, so now when you declare this array of doubles, it will have 5 elements in it. Now, when we declare something of size, right? When we give an array a size, we always use an integer number. We can't have 5.2 elements in an array, 1.6 elements, right? We have whole numbers only. So whenever we declare the size, it will always be an integer number. And then similarly, the other example, we used a pound define, we used a constant. You can use a non-constant identifier as well. Right, so this is non-constant simply because it doesn't have the keyword const in front of it. It's the same declaration, right? We'll have 5. So we've learned then that you can use a non-constant identifier, a constant identifier, and a preprocessor directive, all as names to declare the size of an array. Right. Now here's a question, is this a valid declaration? Right? If you think about it, we want to have positive numbers. Right? If a size is -5, well, we really can't have negative array elements. We have to have a whole number of elements, 0 or more, always more than 0. You don't want to have one that has 0, right? But the thing is, the question is this going to make some sort of warning? If we actually make a mistake and have a variable that has a negative number in it, will that give some sort of warning? Let's actually just take a look at that. All right, let me bring up code blocks here. All right. And so our example then was, we said int a size, we set that equal to -5, and then we declared an array of doubles, array a size. Right. And all right, now I'm going to compile this. And you see, it did not give me an error. It actually just gives me a warning because I'm not using this variable anywhere based on the warning conditions I compile against, at the flags that I use. And you can see then the point of this is that it does not provide a compiler error or a warning. So we always have to be careful, like everything else when we write code. Sometimes the compiler lets us do things that we really don't want to do. Right, so just always be careful of what might be stored in your variables. Right, now, so we can't guarantee that we can't have a negative memory space. There really won't be a negative memory space. We're really going to have some unpredictable results there. It all depends on your application, other variables in your program as to what might really happen. Chances are at some point your program is going to crash. Right. Array subscripting. Well, a subscript is another word for index, right? We call them indices or subscripts. So we use that to access the individual array elements. Right, when we declared our array of size 5, or in this case of size 7, as we saw on the first slide, we say index 0 to get to the first element, index 1 to get to the second, index 2 to get to the third, and so on. Index 6 to get to the 7th. So the last index value, as I said, is always one less than the size. Right? Now the compiler doesn't check the validity of your array index. So if you accidentally type an array index that's out of bounds, the compiler won't give you a warning. What will happen is you'll often overwrite other memory in your program. Sometimes you'll try to write beyond your program's memory limit and your program will just crash. So we always start with 0. That's our first index, right? And they go from 0 to n-1. They have to be integers or some sort of an expression that evaluates to an integer. Right? We don't want them to be negative. And like I said, we'll see some examples where if we go beyond the bounds of our array, the compiler won't necessarily warn us. Right. So in this case, I'm declaring an integer array with 5 elements. I do that. There's the data type int. The name of the array is A. The 5 in the brackets says reserve 5 spaces. So now I have 5 integers in memory that I can all refer to by the name of A. Right. When it creates the array, just like other C variables, they're filled with unknown garbage, right? If we don't initialize it to something, we don't know what's stored in there. But if I wanted to store something at subscript 2, so in this location, if I want to store the number 42, I say the name of the array A, the index location 2, and assign it the value of 42. And in that case, it will overwrite the memory and store 42 in there. So anytime we want to get to any one of these individual elements, we'll refer to them by the name of the array and then the subscript. Right? And the subscript has to go inside the square brackets. Right, so here's some more examples. In this case, I'm going to be storing data in the array, or I'm writing to the array using the assignment operator. So now we have an array of unsigned chars. The name of the array is called myArray. It's 5 long. So if I want to store 9 in the first element, which is index 0, I say myArray at index 0 inside the square brackets. I assign 9 to it. This one will be stored at index location 4, which is the 5th element. Right, this one will be stored at index location 5, or will it? Notice I have a note here. It says illegal, beyond the array bounds, the behavior is undefined. Right, so the compiler, once again, this is what I mean by the compiler will not check to see if I have something out of bounds. The last legal memory location for my array, if my array is set size n, where n equals 5, is n minus 1. So 5 minus 1 is 4. That's my last legal location. If this is beyond my program's memory, it will crash. If it may write over another variable in there. It all depends on how we write our program. Same way, if we want to read information from an array, suppose then I want to read some information from my array at index 4 and store that in another variable. We use the same notation, the name of the array and the index location number, the subscript number, and we can use these in numerical expressions. Right? In this case, I'm pulling this information from memory and assigning it to another variable. Now we can't initialize them, right? We just said if we didn't initialize them, they were full of garbage. Well, when we first create them, we can initialize them. So it has to be at the time we declare. Right? And in that case, we provide what's called an initializer list in curly brackets. Right? They need to be constant expressions. Right? And they need to be separated by commas when there's more than one. So here's an example. If I declare an array A that's of type int, that means it has all integers in it. Every single element is of type int. There's 5 of them. So I've got 1, 2, 3, 4, 5 ints here. And then if I want to initialize them, inside the curly brackets, I have this list of values. The first value in the list is assigned to the first array element. So 77 is stored at A at index 0. 19 is stored in the next element, A at index 1. Minus 13, A at index 2. 5, A at index 3. And finally, the last element, A at index 4. Right? So you can initialize every single element, or you can just choose certain elements to initialize. So here's a case where my initializer list is shorter than the array size. My array size is 5. I only have 2 numbers in my initializer list. So what it does is it always assigns the first thing in the list to the first location, second thing in the list to the second location, and then it fills everything in the rest of the array with zeros, which can come in handy then if you want to initialize an entire array to 0. Now here's the other thing, is if you have an initializer list, you don't have to declare the size. Right? Before, in that earlier slide, when we said we couldn't have int a semicolon all by itself, that's because there was no initializer list. But now with the brackets, here, the empty brackets, my list tells the compiler how much memory to allocate. So there's 1, 2, 3, 4, 5, 6 elements in my list. It will create an array named A. It will reserve 6 elements, so 6 ints in memory. And then it will initialize each one of these elements with the numbers in the list. Right? We usually don't do this. Normally what we do is we know the size ahead of time and declare that. So you won't see this written as much. I won't really encourage you to use it in this class, but it is legal if you see it somewhere else. Here's the most handy thing in terms of initializing. If we want to initialize an entire array to 0, right, so I declared this array named A, reserve 6 spaces for it, 6 elements, right? All of them are of type int, all the same data type. Now, if I want to store zeros in all of them, I just need to put 1 in the list, because remember when we said when the list was shorter, it fills everything else with zeros? Technically, what it does is it assigns 0 to the first one in the list, and then we said if the list is too short, it just assigns 0 everywhere else. So that's nice. If I have an array of 100 elements, I don't have to type 100 zeros into my list. I just type 1, and the whole array is initialized to 0. Now, that only works with 0, right? It doesn't work with any other number, right? If I were to change this to a 1, it would fill this with 1, and all the others would still be 0. So that only works for zeros. It'd be nice if it worked for other numbers, but that behavior is not part of the language. Right? So we might find this handy from time to time. Right? If I want to initialize each element of an array to some other number, in this case to -1, I'm going to declare an array of length 100. Right? So length 100 down here, my array I'm naming A. I'm saying reserve or make it of size 100, so 100 integers. There's its data type. To initialize each one to -1, if I did that with an initializer list, I'd have to type 100 -1 separated by commas. I don't want to do that. Even with copy-paste, I don't want to do that. Typically, what we do then is we use a loop. We're going to use loops to iterate through arrays all the time. I've got a for loop here. Right, so I say for, I'm declaring I in here, setting I equal to 0, as long as I is less than 100, so it will be 0 through 99, this condition will be true. I'm going to store -1 at A at index I. Right, first time through, this will be A at index 0. Right, next time through, A at index 1. Let's actually just take a look at that running in a C example, so you can see how to write a complete program to do that. All right, so we've got our array of size 100 here. Right. We're going to then fill the array. So fill the array with, initialize the array. Initialize all array elements to -1. For int I equals 0, I less than 100, right, plus I, and I just simply need to say array index I and assign that to -1. Right. Let's compile. All right. It's telling me that I've stored some information in A. It gives me this warning and I'm not using it. Right? I'm just doing this for an example. And let's do a run to cursor here. We should build. All right, so it's created an array an array A here. Sometimes code blocks is good and we'll show you all the elements. So in this case, 100, we can see that there are various values in here. Right? Those are all garbage values. I has not been initialized either. Memory's been reserved for it. When our for loop starts, remember that this statement executes once and only once. So we'll store 0 and I. We'll compare then I to 100. 0 will be less than 100. Remember, whenever this condition is true, we come in down here and execute the one statement in the body of the loop. So let me go next line. All right. So we can see I became 0, that passed the test, A at index 0. So here we can see A at index 0, then we stored a -1. The loop comes back up here. As soon as I hit next line, it'll increment I by 1. Right? I will become 1. 1 will be less than 100. It'll go through the loop again. So next line, right? I was 1. We can see, we can watch as I keep saying next line as this flows through our loop that we keep initializing all of these array elements. All right. So we don't want to watch this go through 100 times. If I bring the cursor down here and say run to cursor, it will finish the loop. And now it just tells me that this -1 repeats 100 times in there. So it's not showing me the whole array anymore. It's telling me that all of the elements happen to be -1. All right. Notice now when I'm down here in my code, we no longer see I as a local variable. That's because we declared I inside this for loop, right? And it's now out of scope. Right? We can no longer use I after we come out of this for loop because it only exists right here where we declare it. When the loop's done, it goes out of existence. So let me stop the debugger. Had I declared I here and not here, now if I say run to cursor, I will still be in local memory. All right. So notice I is in local memory. It's equal to 100, right? That when I became 100, this condition was false. It came down here. So when we declare it outside, right, we declared it inside main's memory, inside the scope of these curly braces. So until this function main ends here, I will be in existence. Right? All right, so that's it then for initializing an array to all -1s. And it wouldn't have to be -1, right? We could make this any other value we wanted to initialize that array to. All right. Let's take a look at how we're going to input information into an array from the keyboard. Right. We're going to use scanf, right? That is our function to read from the keyboard, to read from the standard input stream. Right. So we want to write a program that does that. We're going to use a loop to access all array values. What you should be realizing now as we go through these examples, we're going to be using loops all the time with arrays. Right? If we want to perform an operation on multiple array elements, a loop is the best way to do that. All right. So let's actually, all right. I'm going to copy this. We're going to throw this in code blocks and take a look at its behavior. All right, so I used a pound define now, a macro, and created array size that's 5. So here, this is going to create an array named A. There's the name of my array. It's going to be of size 5. Right. It's going to be all integers. And now I've got a loop here. I'm going to set I as my index for the array. I equal to 0 as long as I is less than array size. So as long as I is less than 5, we'll come into the loop. So we have 2 statements that we execute in the body of this loop when this test condition is true. Right, we're going to print out a message, enter a value for A at %D. Well, I'm going to show the value of I. So we'll see A at index 0, A at index 1, A at index 2. Now here's what we want to see then with the scanf, right? Because this is an integer data type, but we know then we need to use the %D for ints. And now we give this the address of array A, so of A at index I. So we have to give it the address of that element. So notice once again with arrays, we're using the subscript notation. All right, let's just do a build and run. All right, so you can see it pops up, enter the value for array index 0, that's our value of I. Right, I can put in any integer value. Right. I'll just go through and prompt me to enter those for all 5. Like I said, the point of this example was to show that when you want to use scanf to store information in here, we give it the address, we use the array name, and then we have to use the subscript location so it puts it in the right place in our array. Now here's something we can't do. You might be tempted to do. You can't assign one array to another. So here we have an array named A1. It's of size 3, we initialized it. Now we're declaring another array named A2 of the same size, A3. You cannot say, let's assign A1 to A2. That doesn't work. It would be nice if it did that and copied the data for us, but that doesn't happen. We haven't learned about pointers yet, but really, the name of an array is a symbolic reference for the address of the first byte of the array. So when I use the name A1 all by itself, that's really is a pointer to that memory, that memory, right? Which is a pointer is a symbolic reference for the address. It's like using the address. These index locations, when we use them, they're offsets from this beginning address, right? And so when we try to assign A1 to A2, it's like trying to make A2 point to the same place in memory. And we can't do that. That's just illegal in C to do that. So we have to remember that array names are constant pointers to memory addresses. Once we declare A1, we can't make it point to any other memory, any other array. Once we declare A2, we can't make it point to anything else. So this operation of assigning one array to another is illegal. They're known as constant pointers to memory addresses, and they cannot be changed anytime during program execution to point to any other area of memory. Now that probably will make more sense later when we start working with pointers. But just remember for right now, you can't assign one array to another. If we want to actually physically copy data from one array to another, then this is the way we have to do it. Right? We have to actually then, in this case, I created this array named A1, right? Put the numbers 1, 2, 3, 4, 5 in its memory. And in order to copy those into array 2, I use a loop. right? Where I just go ahead, we start at I equals 0. As long as I is less than the number of elements in our array, we're just going to copy from one index location to another. So that's how we have to copy array data. We don't have any magic function or anything that just copies it over. All right, let's go ahead and take a look at that in memory. All right, here's our program. Let me just build this. All right. I'm going to do a run to cursor here. All right, so we've executed these lines of code. We should see that A1, so A1 has our numbers in our initializer list assigned to the locations. A2 just happens to have garbage in it. Right, but now as we step through here, right, line by line, we can see now that A at index 0, I0 is going to be assigned. So A1 from index 0 is assigned to A2 at index 0. Right, if we run back through here, we'll watch I increment. We'll just watch these be copied from one to the other. Right, so once again, that's how we copy things in an array. Right. Right, so that's the end of our discussion so far on single dimensional arrays. The next lecture will cover multi-dimensional arrays.